we're going to be recording. All right. So, oh, hey. Yep, welcome to the second lecture in this series of online lectures that we're going to do. Before we get started, just a little bit of bookkeeping or housekeeping that we should be doing. So, as you all know, or at least as I've been getting emails about, we have an exam scheduled for next Thursday, right? So next Thursday we have an exam, and what I am almost certainly going to do, but we're still getting emails about what are the best practices for how do you handle exams. Did the colors get weird, or is that just on my screen? How do the colors look?
I think that's just on your screen.
That's just on my screen. Okay, good. All right, well then I'm fine with that. If it's just on my screen, holler at me if something looks weird. So I bumped something, and I guess my my wiggly camera connector got off. But yeah, so it looks funky to me, but as long as it's reasonable to you, we're okay. So the exam is just going to cover, like last time, 3 chapters, right? It's going to have the same sort of format because we've covered 3 chapters. We've only covered half of the stability chapter. I wanted to cover the whole thing, but we didn't have time to cover it. So we're really going to be 2.5 chapters, right? On the exam, we're going to have exam. It's going to cover observability. Right, so what did we cover? Observability, minimal realizations, and observability, minimal realizations, and stability. And so the format is going to be very much like we had on the last time. 3 questions, multi-part, ABCD. Gonna be, or probably just ABC. Did I just do ABC last time? Or was it ABCD?
It was ABC. Parts.
ABC, yeah. So it's 3 parts. ABC going hard to, easy to hard. Same deal. Only on stuff that we've seen homework on. So, yeah. So I'm not going to throw anything at you that you haven't seen, but things may be hard just because that's what it is. And the way I'm most likely going to do it, people keep talking about using various apps like Proctorio and all this kind of thing. Have you had to use Proctorio at all for other classes? Did anybody do that? Did anybody use Proctorio?
No, I haven't used it. What they did for us is they had a Zoom lecture open if we had questions, but otherwise it was pretty much fill out the test on the computer and then submit it on Canvas within the time period.
Yeah, that's perfect. That's pretty much exactly what I was thinking. That's what other faculty had told me roughly that they have done. And so that would be the plan. Basically, right when the test time starts, I will email you the exam, maybe like, I'll email you the exam, and then you have your time to complete it, and then you stop your things and turn it on in.
I think there's a way of having it open at the specific time on Canvas.
Ah, that's perfect. Okay, yeah, I see. So Canvas has a thing where, oh yeah, exactly. You can have it. You can set a window like unavailable from window. And so then once you hit that time, then it becomes available, and then and then it stops being available. But at that point, we'd already have the PDF afterwards. But I want you guys to be turning it in, within 5 minutes of the end time, basically. So 5:15, I'd want you to have it. I mean, not 5:15, 5:20, say, I'd want you to have it turned in. So stop working at 5:15, but if you're having trouble with the upload or something like that, I don't want to have to deal with that. So just give you out till 5:20, but it has to be in by 5:20. That would be sort of how I make this roll. And then, yeah, that sounds like a perfect arrangement. So that's what we're gonna do next week. All right.
So is
Um,
the test going to be something like last time where we have to do it pen and paper, or is it going to be something that we can do on the computer?
oh, that's a great question, actually. Yeah. Huh.
I had a class where the professor had us write it down and just scan in our responses or take
That's what I was
pictures.
thinking of having you do, really. Yeah.
Yeah. And I'm asking because scanning always takes longer than expected.
Oh
And
yes, you're completely right. You're completely right. So yes. So here's what I would shoot to do then. What do you think would be the best option for this? Because I don't want to be stretching this into like make this thing run really late, basically. So would it make sense to just make a shorter exam and give you 60 minutes to do the exam and then 15 minutes to scan it in?
Yeah, so like this afternoon, basically the professor gave us an extra 15 minutes to turn it in. So I think that's enough.
Yeah, so yeah, what I could do is I could what I could do is I'll just give you an extra 15 minutes, so till 5:30, but it has to be in by 5:30.
That seems to have worked.
What's that?
That seems to have worked with other classes that have done similar things.
Perfect, then that's how we're gonna roll. So we're gonna have the normal length exam time, so we'll set it up on Canvas so it becomes available right when the exam time starts. You write everything on paper, and then you got 15 minutes to scan it in. All right, cool. So that's it. That's how we're gonna do this. Thank you for pitching in on this because it's sort of like I hear bits and pieces on email threads from professors, but I don't exactly know how they're implementing it. So this is very helpful. Cool. So that's how we're gonna do it. Any other questions on the mechanics of this exam? It's gonna work pretty similar to the other exams, right? You know, open note, open book, whatever. Obviously, I can't see what you're doing, so we got to kind of be honor code here that you're not going to be talking to each other. That's the main thing. I'm not even going to worry so much about calculators and so on. Whatever. If you got them, whatever. Uh, because this is nothing I can really enforce. The main thing I just want, I'm going to set it up so that, having a calculator or even MATLAB or whatever isn't super helpful because it's going to be mostly conceptual. So the only main restriction is I want you to not speak to each other. Does that make sense? Just because.
Yeah, quick question. Are we going to have any Python coding in it?
No, there's no way I would ask you to code on an exam. Yeah. No, the Python coding, so people get a little bit thrown off by this. I do this because it's a useful skill. All right, like I'm not, but like I'm not going to be asking you to do it on the fly because I know there's hardly any of you who have ever done it before in your life, right? There's maybe like 3 people in the class that actually know how to use Python. And then the rest of you are all in the same exact boat of like having never seen this before. So no, I would not make you do it. That would be too much. Yeah. So
well, I guess I just want to ask, is it like we're not supposed to use calculators, but you can't really enforce it, or we are allowed to use calculators? And the reason I ask that is like, if you give us something where we're trying to prove observability or whatever, and I say, okay, well, the rank of this matrix is n, therefore, but with the calculator, I could just type the matrix in and, it would spit out the rank. And then that would be enough for me to prove that that was the rank on my end, but on your end, you might not believe me if I just say that. So that's what I'm.
Yeah. No, this is an extremely good point, and this is something we'll have to deal with. So I'd like to take a poll from the class, and you can enter it you can either enter it into the chat or just holler out, because there's a lot of people. I know your name kind of shows up, but like when you raise your hand, your face shows up in class. Who would like to be able to use whatever computing device they want? Who wants computing devices and who wants no computing devices? Everybody,
Sorry, how are we?
say yes if you want the computing device.
Yeah, I would want that.
Yes.
Yes. Okay, I heard 2 yeses and no responses on the chat. Who says no computing devices? I see 1 no on the computing device. I see many no's on the chat. So no's overwhelmed it by a lot. All right. So this is going to be something that you will have to do. This is going to just be an honor code thing. Okay, everybody? So meaning that like, and Nathan brought up this really good point, is that if you just used a computer and said the rank is 2, like I would not believe you if you just like that you could just, unless it was like a very specially structured matrix, I wouldn't believe you that you just knew how to compute that just by looking at it. So you'd have to be able to show your work anyway. So I think the no computing devices is fine, and I'll set it up so that you've got to explain your work, so it won't really help you that much.
So I mean, if we had to, since we have to explain our work anyways, like since we have to explain our work anyways, obviously to get credit, like how much is that really benefiting us? I guess I just
benefit you a little bit, because I've had situations where people use, like when I've done tests where people can use a calculator, people would or whatever, right? They would say from the, they would just write down the answer and they would just say from the calculator. And like, what was I gonna say? Like, no, I didn't, your calculator's wrong, you know, like their calculator was right. And so people would do that when showing their work, but if I make it so that you have to show your work, having the calculator, you have to show your work and you can't just say from the calculator, then it doesn't really help you that much. And so that sort of solves that problem. All right, cool. Other questions on mechanics of the exam? All right. Well, if there are no more questions, we're going to pick up where we left off when we're talking about stability. All right. So where we left off last time was we had this main theorem on stability. So today we're going to review linear system stability. We're going to talk about Lyapunov methods. And these are closely related to energy, which you have to do in your homework. And finally, bounded input, bounded output stability. Bounded output stability. All right, cool. So those are the 3 main things that we're going to do today. And of course, one of those things is just review. Now, are those letters readable?
Yes.
yeah, they are. It's just there's a little bit of glare at certain points, but otherwise.
Right. Yeah, I have a really hard time with the glare. I've been trying to figure out a way to make that not happen so bad. Part of the big issue is I got this light right here. Let's see if this helps. How does that look? Or is it too dark?
Seems like it's mostly coming from the other side, actually.
Okay.
I think that's a bit better. Definitely better than before.
Well, so let me know, and I'll adjust as we go. All right, I'll adjust as we go. So recall that what we saw last time, the biggest thing that we saw last time the takeaway, we went into a lot of gory detail about things like geometric multiplicity, algebraic multiplicity, and so on. But the big, most important takeaway message is if the real part of lambda is less than 0 for all eigenvalues lambda of A, then x of t goes to 0 as t goes to infinity, where x dot of t is equal to a x of t, right? That was the big thing. So this is an asymptotically stable system. We say that 0 is an asymptotically stable equilibrium, or sometimes simply, this is an asymptotically stable system because asymptotically this is going to 0. So it's not blowing up. And we saw that in other situations, we could have things just stay bounded. That would be marginally stable. And then finally, things could blow up. But typically when we're doing controls, at a baseline, we want to design our systems so that they're asymptotically stable. So in the end, we study stability analysis of systems with no inputs a lot, because in the end, we're going to design inputs so that when you plug the inputs back in, you get a closed loop system that is asymptotically stable. So it's just good to understand this thing right here. Yeah, that's the main piece of stability. Now, Lyapunov methods are a generalization, or Lyapunov functions are a generalization of energy functions. So in your homework, we studied a system that looked like this. So in the homework, we had a simple harmonic oscillator. And the simple harmonic oscillator had equations of motion that looked like this. And x of t. And what we have is when the eigenvalues, real parts of lambda, the eigenvalues are less than 0 when zeta is greater than 0 and omega naught is greater than 0. So in that system that we looked at, we have this condition that when these coefficients, the damping and the natural frequency, are positive, this system is asymptotically stable. So depending on how you choose these values, you could have either 2 real eigenvalues or 2 complex conjugate pair eigenvalues. In either case, the behavior is such that no matter where you start from, you go to 0 and you get there exponentially quickly. Now, what I ask you to do in your homework is compute the energy of this function, the energy of this system. So the energy of this system is the following thing. So this has the same form of a spring mass damper system, or really an RLC circuit, where these guys are sort of generalized sort of non-dimensionalized coordinates that tell you something about the parameters of the system. In either case, the energy of the system is really given to us by 1/2 x2 of t squared plus 1/2 omega naught squared x1 of t squared. And what you'll see in your homework is that the energy is decreasing in this system. And let's go and look and see what's going to happen with the energy of the system. In particular, we're going to look at the time derivative. Actually, I think I might have asked you to find the time derivative of energy in your homework. I mean, I derived it for you, so maybe I'll kind of tell you what it is. I'll get you most of the way there. d dt, e of t, in this system, right? this thing is really a function of the state. We can write this as energy So if I wanted to take the derivative of this thing, what rule would I use? It's a rule that rhymes with the brain rule. It's the chain rule. None of this works nearly as well online. All right, so the chain rule would tell us that what we do is we take dE dx dx dt, right? That's the chain rule for this thing because this e only depends on t through the state, and so chain rule gives us that. And this thing is just equal to dx dt. This is dx dt, so it's equal to that. So I can write this thing down as omega naught squared x1 of t. So I'm taking the derivative of this guy with respect to x1, the derivative of this guy with respect to x2, times, oh, I forgot the 1 here. Why didn't James holler at me? I needed a 1 up there. All right, and then times ax of t. This thing is, of course, ax of t. So I can plug this guy into here. One negative 2 zeta omega 0 times x1 of t, x2 of t. All right, now let's see what this thing's actually going to do, right? If we go and write this thing down, right? We're going to get up in here. It's going to be omega naught squared x1 of t, x2 of t times x2 of t times negative omega naught squared x1 of t minus 2 zeta omega naught x2 of t. All right. And then when we do this multiplication through, I'm going to get an x1 times an x2 minus this thing. Let me just do it explicitly. x1 of t, x2 of t minus x1 of t, x2 of t. So these are the exact same thing. They cancel out. Minus 2 zeta omega naught x2 of t squared, or simply minus 2 zeta omega naught x2 of t squared. All right, so now what this is going to tell us here is one conclusion that we can take away from this system is that energy never increases for this system, right? Energy never increases because if this guy is positive and this guy is positive, this is a negative number. So the derivative of the energy, which is telling you how it's changing over time, is always this quantity, which is less than or equal to 0. It's only going to go to 0 when x2 is equal to 0, right? But if x2 is equal to 0 and x1 is not equal to 0, so let's just think about this. What's going to go on here? It's never going to get stuck there either. So you're going to plot a simulation of this thing. You're going to plot a simulation of this thing. So we have a simulation of this thing, and it's going to look something like this. We showed our simulation in x1, x2, and in the homework we see it's going to go like this. And what's going to happen is, as this thing is traveling along, the derivative of the energy is, when x2 is non-zero, the derivative is always strictly negative. Occasionally, it's going to go through these points where the derivative is 0. okay? And but then it's going to start getting back up again. So then, which is, I mean, it's going to start decreasing some more as soon as it gets kicked off there. The only time it's never really going to stop until it finally gets really too close to the origin. So if we do a plot over time, it should look something like this. T, our energy should be decreasing, and then it'll might maybe come to it'll come to zero, and then it'll decrease some more, and it's not going to go negative. Sorry, it's just going to keep doing this where it goes, it decreases, it decreases, it decreases, and then it keeps going down to zero, just like that. But the key takeaway thing is this is monotonic. It has sort of tiny little points that stops decreasing, but it's essentially decreasing strictly the whole time. And that insight there was something that people generalize a lot, like way back in the day, like hundreds of years ago or something. That if you have a system whose energy is decreasing monotonically, the thing's going to be stable, meaning that, you know, if the energy keeps getting smaller, you can just look at this energy function and use it as a proxy for stability. Because if we look at this energy function and we know this thing is decreasing, all right, when this thing is zero, the only way that this can be zero, if this is a positive number, is if x1 is zero and x2 is zero. So we have e x of t goes to zero, and if e x, which is equal to 1/2, I'm just going to write it a little bit different here, x1 squared plus 1/2 x2 squared is equal to 0, we must have x equals 0, x1 equals 0, and x2 equals to 0. So this gives us a way, a proxy for studying stability of systems by finding an energy function for the system. If we can show that there's some energy function that has this property, namely that it's strictly positive for non-zero values, then we know that if we see that energy function is decreasing monotonically and going to zero, we know that the system has to be stable and going to zero. And so one of the big reasons that we study these things, there's a few different reasons. We can actually use these tools in control design where we're saying, okay, I'm going to pick an energy function and I'm going to design a controller that has that energy profile. That's one thing that can be used for. And the other thing that's really nice about this is that condition we looked at for linear systems with eigenvalues is only valid for linear systems, right? I mean, only a linear system is everything dictated by eigenvalues. But even for a nonlinear system that may not have any natural notion of eigenvalues other than, say, an approximation near the origin, even for a nonlinear system, there are going to be many cases where we can construct the energy function and show that it's decreasing. In particular, for typical mechanical systems that you might see in robotics, you can oftentimes construct an energy of the system just based on classical potential and kinetic energy. And as long as you have some friction there, you can show that the thing is going to be stable using these energy methods. So what we're going to do now is really see how we can analyze these energy functions using techniques from linear systems theory. So it turns out that this is a very, very well-established, well-developed way of analyzing the stability of the system, but then it's also very useful for analyzing other properties of the system. We'll see some of those in the homework. We're not going to have a homework this week because we got the exam, but then the following homework, we'll see some of these properties. Namely, what we're going to want to do here is, in a more systematic way, analyze the behavior of this energy function. All right? So what we want to do is we want to systematically be able to show that this energy function is in fact going to zero. And the other thing that we're going to do by the end of all this is have a systematic way of constructing things that are sort of like virtual energy functions. They're not actually corresponding to any energy itself, but they play the role of energy and they can be used to analyze the stability of a system. And that's just called a Lyapunov function. But for now, we'll stick with a thing that actually is energy. So the first thing that I'm going to do is rewrite this energy function in a little bit of a different way so that I can get a bit more compact notation. Rather than writing it like this every time, I know that I can actually always rewrite. When I have a quadratic that looks like this, a quadratic form that looks like this, I can go and rewrite it as x1 of t, x2 of t times, and I'm going to put a matrix in here. And this is something that just takes a little bit of practice to see how you actually get the coefficients of this matrix. You just have to do it a few times. But after you've done it a few times, you'll see that if you just read off that there's going to be a matrix here, it turns out that the matrix is not unique, but if you assume that it's a symmetric matrix in here, so there's only going to be one symmetric matrix that is going to make this work out. And of course, because there's two things on this side, two things on this side, and this is a scalar, this has to be a 2 by 2 symmetric matrix. And the only 2 by 2 symmetric matrix that will make this work is this. That is the matrix over here. And what we're going to do is we're going to call this thing x of t transpose q x of t. All right. And now what we're going to show here is we're going to show that we know, first off, we know the following thing. We know that x of t transpose q x of t is strictly positive when x of t is not equal to 0. That is what it means to be positive definite. i.e., q is positive definite. All right? Because what we're saying here is a matrix is positive definite and we're going to denote it by q. And I'm going to use this like sort of squiggly greater than sign. It's positive definite, and this is denoted by if it's symmetric, and of course that thing is symmetric because it's diagonal. Every diagonal matrix is symmetric. And x transpose qx is strictly positive for all non-zero x's. So that's what it means to be positive definite. Now it turns out that somewhat more this is the definition. A somewhat more convenient way of expressing this is here's just a fact or a theorem. And I'm not going to show it. A symmetric matrix is positive definite if and only if all its eigenvalues are strictly positive. Its eigenvalues are strictly positive. So every symmetric matrix has real eigenvalues, and a positive definite one is one in which all of its eigenvalues are strictly positive. So that's sort of a more convenient way of thinking about positive definite matrices, but this is the actual definition. And so and you can see that this thing is positive definite because it's definitely symmetric, and also its eigenvalues are 1/2 omega squared and 1/2, and as long as omega squared is positive, this is definitely positive definite. All right, so that's sort of generalities about this matrix Q. All right, what we're going to do is we're going to show, so this is just an aside on positive definiteness. That's just a definition. You can, there's more to say about those, but we're not going to need generalities just yet. We will, by the end of class, use those a bit. All right, so we're going to show that the integral of 0 to infinity x of t transpose q x of t dt converges. So meaning this thing sums up to something that's less than infinity. So we're going to show that this is a convergent integral. And so what that's going to mean here, so this thing, of course, is just the integral of the energy. And this thing is always positive. So the only way we're going to have something that is always positive for all t if x of t is not equal to 0. The only way that we're going to have this thing integrate out to 0 where it's positive, integrate out to something that converges is if limit as t goes to infinity e of x of t equals to 0. That's the only way that this integral will converge. Because otherwise, if this thing was positive, as t went to infinity, then we're going to get something that integrates to infinity. This integral is not going to converge. All right. So essentially, for this integral of positive quantities to converge, this thing has to go to 0, which that implies limit as t goes to infinity of the state itself. So we've just gone and shown that if the energy has a convergent integral, then this system has to be stable, meaning that no matter where we start from, we converge to 0. Right? So what we're going to do here is go and explicitly construct the form of this integral. In particular, we'll just give a solution to that integral, and then we'll also show a way to compute it that doesn't actually involve computing an integral. So we're going to take a step back and do this a little bit more generally. Say that A is stable. So I don't remember what the book is going to call this, but i.e. its eigenvalues have negative real parts. Real parts. There's lots of ways that people call this. Sometimes they call it a stable matrix or a stability matrix. Sometimes they call it a Hurwitz matrix. Whatever, I'll just call it a stable matrix. It's a simple way of calling it. Hurwitz is because there was a person named Hurwitz that studied these back in the day. Then what we're going to have here is say that A is stable and Q is square. So it turns out that when the thing is stable, recall from the example that we saw before, in the example that we had before, the A matrix was stable whenever we had positive damping and natural frequency parameters. So in general, we're just going to assume that this is a stable matrix and this is a square matrix. That one had specific properties that is positive definite. I'm just going to deal with any square matrix. So this is a more general case than what we were just talking about. This thing, x of t transpose q x of t, this integral dt, we're going to be assuming that we have a system of the form x dot of t is equal to a x of t.
Professor,
Yes?
when you talk about like choosing an energy profile for your system, is that equivalent to choosing the value of
Choosing what?
choosing Q? Sorry.
No.
Or is that?
So what we're going to see actually later, so this was actually kind of doing things a little bit backwards, but it just kind of works. But no, so what ends up happening, it kind of is. Okay, so the answer is yes. But then it's also no. So it is basically yes. We would choose a Q, and then we would go and design a controller to make this integral go to 0. This integral converge. But we're not really going to be doing too much of this. I will show you very briefly how it works after we present Lyapunov equations, and then it'll hopefully be a little bit more clear what I mean by that. All right. So, but it basically is that we would be choosing the Q. All right. Because again, this is, as long as this is stable, this is going to hold for any Q. So if we've got x dot is equal to ax, we know that I can actually plug in the explicit solution to this thing. E to the at x of 0 transpose q e to the at x of 0 dt. And then just by using rules of transposing, if I'm transposing a product, I flip the order and transpose both. The transpose of e to the at is just e to the a transpose t, because it's just, you could just read that off from the power series expansion of this thing. So what we're actually going to get is I can pull an x0 and x0 off to the sides here. And I'm going to call this matrix P. This is just some matrix. Okay? And let's think about why this integral converges. Okay? So when all the eigenvalues have negative real parts, these guys are all just linear combinations of things that are exponentially convergent. You're going to show that in your homework. When they have negative real parts, or at least a piece of that, combined with what we did last week, is that all the entries of this guy are exponentially convergent. All of the entries of this guy, e to the at, are exponentially convergent. If we transpose, we're just reordering the elements. So all the entries of this guy are exponentially convergent. We multiply things that are exponentially convergent, they're still exponentially convergent because you're just gonna, the exponentials just multiply. All right. So all of the terms in this integral are exponentially convergent, which means that you can integrate it, and you're going to get a well-defined thing because as t goes to infinity, what you're integrating just goes to 0 very quickly. And so this matrix exists. Okay, this is a convergent integral. Cool. So we've just shown sort of in this special case that when the system is stable, this integral is indeed going to converge. And so indeed, we're going to have x of t go to 0, but that's kind of obvious, right? It's stable. So of course x of t is going to go to 0. All right. So we haven't really shown anything super interesting yet. But the thing that we have here is that the thing that is going to start to get interesting is that when A is stable, it turns out that we can compute P without actually computing this integral directly. When A is stable, we can compute P without integrating. Right. So in particular, what I'm telling you right here is that we can actually compute the value of this integral without actually doing any integration. And that's where the little bit of the magic comes. So it turns out that theorem, if A is stable, then P is the unique, and I'm only going to show a piece of this, solution to the equation A transpose P plus PA equals minus Q. And this is called the linear Lyapunov equation. Linear Lyapunov equation. Named after the famous Russian scientist Linear Lyapunov. No, it was just Lyapunov, just specialized in the case of linear systems. So, right. So the key thing here is this is actually just a linear equation. It's just a system of equations, right? Where if this is n by n, if this is n by n, and this is n by n, the p is going to have to be n by n as well. And so the uniqueness actually comes down from the fact that by direct construction, so I'm just going to hand wave the uniqueness. This thing is a mapping from n by n matrices to n by n matrices. Given any p, there's an n by n q that comes out. And what we're just about to show here is that given any q, there's a solution to this matrix, and there's a solution to this equation, and so it's going to be an onto linear mapping from n by n matrices to n by n matrices. And so what's going to end up happening is that this mapping is going to be invertible, and that's where uniqueness comes from. But there's a lot of linear algebra going on under the hood to show why that's true. But if you know why, if a finite dimensional linear operation is onto, then it must be invertible, so the solutions must be unique. That's it. That's the hand-wavy explanation for why it's unique. But I will show very specifically why, if A is stable, then P, this thing over here, given any Q, this P defined by this thing over here solves that equation. All right, so I will show that P solves that. So the proof is this. Let P equal to this integral. And as we discussed before, this integral is always convergent. then what we're going to show here is we're just going to do the following thing. I'm going to evaluate this integral two ways. A transpose T, Q, E to the A, T. So I'm going to look at this integral. It's closely related to that integral, but it's not the same thing. All right, so the first way I can evaluate this is by fundamental theorem of calculus. By fundamental theorem of calculus, this is going to be just we just get rid of the derivative in the integral and just evaluate it at the endpoint. Right, fundamental theorem of calculus, Q, E to the A, T, evaluated at 0 and infinity. As t goes to infinity, this guy is going to go to 0, and this guy is going to go to 0. As t goes to 0, this guy is going to go to the identity, and this guy is going to go to the identity, and so it's going to leave us with 0 minus q, or simply minus q. Now, I can also evaluate this via the chain rule, or by the product rule. So by the product rule, there's only two pieces that depend on t, namely this piece and this piece. So I take the derivative of this piece and then multiply it by this piece. And then I take the derivative of this piece and multiply it by this piece. And what I get left with is this. So it turns out when I take the e to the at, I can bring that down, right? That's just the derivative of that. At, e to the a transpose t, q, e to the at. So that is taking the derivative of this piece and multiplying it by that. And then I have to add it with this piece times the derivative of that piece. I can bring the a down to here, but a actually commutes with this matrix exponential. This is a product property that we can see, again, directly from the power series expansion, that ddt of e to the at is a e to the at, or e to the at times a. So I can bring it out the other way. Dt. Now what I can do here is we can see that the only bits that depend on t are this bit and this bit, which is exactly the integrand over here. I can go and rewrite this as a e to the at transpose q e to the at dt plus 0 to infinity e to the a transpose t q e to the at dt. I need an a transpose over there times a, or we recognize that that's just our p. A transpose p plus pa. So putting those two things together, this is just the exact same integral evaluated twice. We see that a transpose p plus pa is equal to minus q. So given any stable matrix, there's always a p that satisfies that, and that p is given by that. And it turns out that just by generic properties of linear algebra, this p actually has to be unique. And so what that actually means is if I'm given a stable system and I'm given a q, I can just construct that p directly that gives me that integral. So in particular, if I've got a stable system and I want to calculate the integral of the energy, I can just plug it into this linear Lyapunov equation. It turns out that these equations show up like everywhere in a lot of pieces of numerical linear algebra. So most linear algebra softwares are going to have a linear Lyapunov equation solver because it can take advantage of the special structure of this equation. So they have very dedicated linear solvers. You could, in principle, just solve this, like set up n squared equations and n squared unknowns and just solve it, but it has extra structure that a lot of linear algebra solvers take advantage of. So in particular, MATLAB, Python, a bunch of other places just have commands for solving that. So in your homework, I'm going to ask you to use the commands to just solve that to compute the energy integrals that we were looking at. Cool. So the next thing to go on top of this, we kind of almost did most of this. So this is sort of the linear Lyapunov theorem. The system x dot of t equals ax of t is asymptotically stable if and only if given any q positive definite, there exists p positive definite. So that's positive definite, meaning, remember, this means a symmetric matrix with all positive eigenvalues. So given any symmetric matrix with positive eigenvalues, there is a solution to this Lyapunov equation. P plus P A equals minus Q. All right, and we've actually gone sort of most of the way, at least in one direction. So what we've shown here is that if it's stable, doesn't matter what this is, this P exists. All right, but we haven't shown that it's positive definite, but so say A is stable. We've shown P exists and is given by P equals 0 to infinity e to the a transpose t q e to the a t dt. But this thing is always going to be positive definite, and we can see that this is positive definite because these guys are actually invertible matrices. So, because remember, the matrix exponential is always invertible. Its inverse is just given by e to the minus 8t. That means if x is not equal to 0, then x transpose px is equal to the integral. All I'm going to do is I'm going to take these x's on either side, do a little bit of that simplification that we did before here, just reversing the steps here. Q e to the a t x dt. And this guy, because this is an invertible matrix and this is non-zero, this thing is non-zero, this thing is non-zero, so that means that the whole thing here has got to be strictly positive. So we're integrating a strictly positive quantity over all time. So if we're integrating a strictly positive quantity over all time, this has got to be positive. Yes. So that's what we're doing here. And so what we've seen here is that this guy's positive definite. So that kind of shows this whole direction. The other direction is pretty straightforward as well. So say P and Q are both positive definite. So we just showed directly the definition of positive definiteness. I take any x on this side, any x on that side. It's positive. And A transpose P plus P A equals minus q. Now, let's take x to be any eigenvector. Let x not equal to 0 be such that ax is equal to lambda x. In other words, this is an eigenvector of A. X is an eigenvector of A. All we're going to need to show, in order to show that this thing is asymptotically stable, is that this lambda has negative real part. That's what it means, because remember, that was the theorem that we had before. It's asymptotically stable if and only if all its eigenvalues have negative real parts. So just take an arbitrary eigenvalue, and we're going to show that its real part is negative, just by plugging in to that Lyapunov equation. So recall that this is the conjugate transpose of this thing, because in general, this could be a complex vector and that could be a complex eigenvalue. So in order to deal with this, we have to deal with conjugate transposes. X. We know that this thing is actually equal to, by pulling this to the inside, this thing is actually going to be equal to, pulling this over here is going to be we know the following thing, ax star is equal to x star a. We're assuming is a real matrix, so you conjugate everything, you transpose it, is the same as just transposing it, because the conjugate of a real number is just itself, A transpose, and this thing is equal to lambda x star. And so then we know that this thing has to be equal to x star, and lambda is just a scalar, so its conjugate transpose is just its conjugate, so it's that. All right, so putting that together, we see here that this piece, when I bring it in here, I can pull a lambda bar times x star px, and then plus lambda times x star px. And I can regroup these terms where if I add, these are exactly the same. If I add a number plus its complex conjugate, I get 2 times the real part of lambda times x star px. And this thing, by using the Lyapunov equation, is equal to negative x star qx. And now, I didn't talk about complex vectors here, but complex vectors are going to work exactly the same here, because if we had, let me just show it really quickly. If x is equal to a plus jb, x star is equal to a transpose minus j b transpose. If this is its real and complex decomposition, now let's just go and look at what this thing is going to be here. X star qx. Q is a real matrix over here. This thing is A transpose minus JB transpose Q A plus JB. And then I can break this down here. This is going to be A transpose QA. And then I'm going to get A transpose QJB. I'm going to pull a J out in the front, A transpose QB, because J is just a scalar, right? It's just the imaginary number right over here. This guy I'm going to get minus J B transpose QA, and then plus B transpose. I'm going to get a J, a minus J B transpose QJB, and a minus J is going to hit that positive J, just giving us a minus, just giving us a positive 1 QB. And then what happens here is this. This thing is exactly equal to that thing, because this is a symmetric matrix. So this actually cancels out with that, leaving us with A transpose QA plus B transpose QB, and that's got to be positive. And this is all coming from the symmetry of this thing, namely that A transpose QB transpose is actually equal to B transpose Q transpose A, where all I did was I transposed everything, flipped the order, but this thing is the same as Q. It's B transpose Q A. So we see this is just taking advantage of a scalar is always the scalar is always the transpose of itself, and so this thing is equal to A transpose QB. So this guy and this guy are exactly the same, they cancel out. So even with complex vectors, positive definiteness still implies that we get this positive thing out here. So returning to what we had over here, I know then, that was just a little bit of a digression. So I know then that this is a positive number and that's a positive number, because I'm assuming that x was non-zero, and so that implies that the real part of lambda is equal to minus x squared px over x squared over qx to x squared px, and this is strictly negative, right? Sorry, it's a positive number divided by a positive number, all multiplied by a negative, so it's negative. So that's the linear Lyapunov theorem. Cool. So we've got 7 minutes. We're going to be shifting gears pretty radically. So I'd like to stop and ask some questions, and then I'm just going to get started on the next bit, but not go too far. Questions? No questions. All right. Cool. So in your homework, we're going to be, I'm going to ask you, this is back to one of the questions that we had before, actually, was how would we actually use this in control design? I don't remember if the book goes into this, but I'll just briefly show how this can be used for control design and how you can actually use this in particular as a design parameter. So this is a preview of stuff that people do in sort of more advanced controls. This is a very simplified version of these things. So using Lyapunov equations for control design. For control design. So the first fact is that A and A transpose, A and A transpose, have the same eigenvalues. So this is a fact that we're going to use. And so any matrix and its transpose always have the same eigenvalues. So, and this is pretty easy to see if you look at the Jordan canonical form, for example. You just transpose the Jordan canonical form, and then you get a lower triangular matrix, but it's still a lower triangular matrix with the same exact eigenvalues on the diagonal. So eigenvalues are the same. All right. So namely, this implies A plus BK. So if we have a system is stable, if and only if A plus BK transpose is stable. All right. So what we're really going to be dealing with here is systems that look like this. A x of t plus b u of t. And this is what's going to be the focus of next week's stuff, except we're probably not going to do it via Lyapunov theory, as far as I know. I don't remember if the book does it like this. We're going to be searching for k to make ut equals k x of t stabilize the system. So in order for this to stabilize the system, I plug this kx in where I see the u. Okay, so if I plug that kx in there, I get an x dot of t is equal to a x of t plus b kx of t, or regrouped, it's a plus bk x of t. All right, so that's the basic problem of state feedback design is you're gonna try to find a k that when you plug it into the system, the resulting thing you got over here is stable. We saw this very, very briefly when we were talking about controllability. Yeah, so what we're going to do here is we're going to apply the Lyapunov equation to this matrix in particular, because we know that this matrix is stable if and only if that matrix is stable. So what we can do is set up the Lyapunov equation. For this matrix in particular, so we're going to get P A plus BK transpose plus A plus BK P equals minus Q. And now what we'll do is I'm going to regroup the terms here. I'm going to set M equals to KP. All right. And so when I've set this thing equal to that, I can go and regroup it. It's kind of easiest to see what's going to go on over here. This is going to be equal to A P plus B KP, but KP is just M. And this thing, I'm transposing it over here. It's going to be P times K transposed. This P is a symmetric matrix. Call that P is symmetric. And so this is going to be KTB. So I'm just using rules of transposing plus PA transpose plus this. I can regroup this as this is equal to M transpose. So because of the symmetry of this thing is actually just M transpose, B transpose plus P A transpose plus AP plus BM. And I'm going to be setting this equal to minus Q. So the design procedure is this. And this comes back to the question that you asked earlier. You can use the Q as sort of a desired energy that you want to minimize. And then what you do is you choose this, and then you search for the P, and you search for the M that satisfies this. You search for P positive definite and M, and then if we find them, that means that it turns out that if you could stabilize the system, you could find the P and the M, and then we would set. Well, all we would do is we would just set K is equal to M P inverse. If you find the M and the P. And so that's how you can use this for control design. So a lot of ideas are built on this and generalized ideas of that. Anyways, I've run over time a little bit. So again, we'll kind of, touch base next Tuesday. All right, thanks. If you got any questions, I'll stick around.
Oh yeah, I have a question.
Yep.
Earlier you were talking about you had ATQB equals ATQB transposed equals BTQT. Can you go through that? Like, well, first off, how did you transpose the whole thing without doing anything else to the equation, I guess?
Right. So right, so this thing, what I was looking at is I had A transpose QB. And I know that this is a scalar. And so a scalar, it's a transpose of a scalar is always just itself. Right? So this thing is always equal to, because it's a scalar, equal to itself. Because transpose a scalar, all you're doing is flipping the indices, but there's only one index, so there's nowhere for it to go. So now I know that this thing, when I transpose a product, I flip the order and transpose everything. So all I did was I took this to the other side, transposed it, kept this where it was, transposed it, took that to the other side, and transposed it. A transpose is just A. But then I know that this thing, the transpose of Q is just itself. So it's B transpose QA. Now is it?
So how did that relate to the X star QX thing?
Oh, yeah. Because what happened was this. The imaginary part, if X is equal to A plus JB, this thing is going to be having a real part, A transpose QA plus B transpose QB plus J, A transpose QB minus B transpose QA. But this thing is just that, this thing is just that, and these are exactly the same. So that part goes to 0.
Okay, I see. I didn't catch that there was those two additional terms that canceled out. I think that
Yeah,
was.
that was the whole point of doing that, is to cancel those. Yeah, so that's why we did it, is to show that these guys cancel out, and so that what we get is, even if we've gotten complex eigenvectors, what we get when we do this product is something real and positive.